Hello, I'm Derivation, and welcome to our second installment of Math Matters, the golden ratio series, in which we're talking about the golden ratio phi and how it applies to our everyday lives. So, in this video, you asked for it, here it is. This is the down and dirty secrets as to how we get that number right there, and the mathematics behind that derivation, that very important derivation of phi, right? Phi, our golden ratio, right up there. It's the Greek symbol, which I wrote over here and wrote it bigger, a circle with a line through it. Now at this point, if you haven't seen my first video introducing the golden ratio, talking about what it is and how it could be important to our society and our daily lives, I recommend you watch that right now. And if math isn't your thing, I encourage you to watch it. I still encourage you to watch this video and that video. Of course, this video more so is the proof of why it is that number. All these videos are kind of fighting the bias against mathematics and showing that really does apply. What you learn can apply. Here we're going to talk about the quadratic formula, which many high school students are forced to learn and tested on. But we're going to show how all the things I'm going to talk about the golden ratio are all rooted in mathematics. So let's get right to it. The golden ratio is only magical and special if this proportion is true. A over B equals B over C. And if you watch my last video, you'll know that A is this big segment we have here, and we split it into two segments, B and C. B is the larger division, C is the smaller division, by definition. So the big segment to the larger division is equal to the larger division to the smaller division. Because this proportion is true, and because we know that's what defines phi, our number, we're going to prove that it is 1.618. How do we do that? Well, if we set this ratio as phi, the easiest way to do that is setting it as phi over 1, right? Phi over 1 is a fraction or a ratio, but it is phi by definition. Anything divided by 1 is itself. So phi over 1. Let's call phi b, and then c would be 1, just because b over c, and we don't want to call a phi because a is split into parts. So b over c is phi. There it is, there's the proof. Phi over 1 is phi. Okay, so far so good, but we still have a. And a is by definition made up of b and c, so we add together, made up of addition of segments. So we add the variable and the number. 5 plus 1, that's alright. So let's rewrite the proportion, and let's prove it. Let's prove it's this number. So we rewrite the proportion as, I'll write it down, get out of the way. Phi plus 1 over phi equals phi over 1. Phi plus 1 over 1, a over b. A is phi plus 1, b is phi, and the same for b over c as I've explained it. So here's where algebra comes in. We're going to cross multiply. Now, cross multiplication is a very useful tool that you learn in algebra, and I'll show you why. This, if you don't know phi, look how many phi's there are. There's 3 phi's. You can't add them up or anything because they're in fractions, and dividing by this weird ratio you don't know is very hard until you multiply across. That way you get rid of the fractions. Here the fraction's 1, you get rid of that easily. Get rid of phi easily, and then you're on a better path to solving for it. So let's cross multiply. 1 times this whole thing is going to stay as it is. So 5 plus 1 stays on the left. On the right we have phi times phi. Now what's phi times phi? Well, what's 2 times 2? 4, right? What about 5 times 5? 25, and then 22 times 22 is 22 squared. So, when we have a number that we don't necessarily know the square of, we can just call it squared. So x times x is x squared. Phi times phi is a variable here. We don't know what it is yet. We're trying to prove what it is. We don't know what it is. So phi times phi is phi squared, right? That's why we're going to use the quadratic formula. So right now we have a quadratic, right? But we can't plug it into this because we need it into a form where a quadratic equals 0. So let's move everything over to this side by subtracting. To move it over, we have to subtract so that we cancel it out. So subtracting phi, subtracting 1, these cancel out, subtract. That means that we have to subtract phi and 1 on the other side to keep it equal. And our handy back pocket eraser, these all cancel out. And this whole side becomes 0, sorry. Anything minus itself is 0. Much better. So, what does this mean for the quadratic formula? Well, quadratic formula uses A, B, and C. Well, at this point you're like, Ricardo, I don't see any A, B's, and C's. Are those A, B's, and C's? No, these are very different A, B's, and C's. These are capital A, capital A, capital B, capital A, capital B, and capital C. What these mean are the coefficients of our terms. I'll explain what that means in a second. So, A is how many phi squares we have. We have 1's phi squared, right? So every time I see A, I'm going to plug in 1. B, how many phi's we have, the second term. We have negative 1 phi, because it's minus phi. So negative 1 and minus, same thing. And C is how many numbered, like what is the numerical constant we have at the end, and it's negative 1. So, phi, our variable, equals the quadratic formula, because the quadratic formula is the solution for the variable in your quadratic. Here it is right there. Let's plug in the numbers. B is negative 1. So, it would be here. It would be here. That's negative 1, negative 1. And then we have two A's. A is 1, as I showed down there. 2 times 1, 4 times 1. And then C is negative 1. Then times negative 1. Okay, so negative 1 times negative 1 is positive 1. And the reason for that is, well, your math teachers teach you a negative times a negative is positive. But if you don't like that, think about English, right? Although it's not grammatically correct, a negative is a positive. So if I say I'm not going to go to the baseball game, I am going to go to the baseball game. I'm just not going to avoid it. And double negatives can't be used, but they're really good examples. Same thing with negative 1 squared, right? Negative 1 squared is just two negatives times each other. And a negative times a negative is a positive. So negative 1 squared is 1. And then we do this. Negative 4 times 1 is negative 4. The 1 doesn't matter. But negative 4 times negative 1, that becomes a negative times a negative again. And the 1 doesn't change the value. It just changes the sign. So negative 1 is 1 plus 4 in the square root. 2 times 1 again doesn't matter, right? The times 1 doesn't change it. So we have 1 plus or minus the square root of 5 over 2. Now, why plus or minus? Ricardo, you only wrote one number, some people might say. You only wrote one number. You're telling me I can do plus and minus and I have two solutions? Well, yes, there are two solutions to any quadratic, because you have to think about, well, if phi is positive, it's one thing. If phi is negative, it's one thing, because negative 2 squared and 2 squared are both 4. That's the weird thing about squares and quadratics. But because we define phi in terms of length, in terms of a line segment, we can't call phi negative. Phi can only be positive, because line segments can only be positive. And that right there takes away our negative. So we can only do 1 plus square root of 5, because square root of 5 is bigger than 1. Square root of 5 is, I don't know, about 2 point something. So 1 minus 2 would be negative, divided by 2, still negative, and phi has to be positive, because remember, this is all phi. Now that we have solved for phi is 1 plus the square root of 5 over 2, we've solved for the golden ratio. Plug that right into your calculator, you get phi, as denoted by this, is 1.618, and we're done. That's how you mathematically prove phi, the ratio, is 1.618. Hi guys, thank you so much for watching my video. It really does mean a lot. And if you enjoyed this one, I encourage you to watch the next video of my series. And hey, if you're done with the series, there's always more mathematics to learn. Because remember, math matters.